Hi students, welcome to Science Extension and Module 3, the Data, Evidence and Decisions. This is video number 5 and we're going to talk a little bit about assessing data. What you need to be able to do is to assess the relevance, accuracy and validity of the data and determine any error, uncertainty and then comment on its limitations. So this is a lot of considerations for the assessment of your data, and it may seem a little early in the piece to be trying to do this, but if you keep in mind some of the key issues that are associated with data collection and interpretation, then hopefully that will help inform you as you do this process to make sure that you are considering all of the key aspects of data assessment. So we need to make sure more than anything else that our data can be used as evidence to evaluate our hypothesis. Remember at the beginning of this section, we did talk about the difference between data and evidence. And so if we're going to turn that data into evidence, we need a context, and that's our hypothesis. And we need to make sure that the data that we've collected is actually going to tell us something meaningful about our hypothesis. Whether or not we reject or accept that hypothesis, we do need to make sure that our tests are legitimate and scientifically reasonable. There's several tests that we can use to interrogate our data so we can make a judgment of its efficacy. When we consider our data and how we're going to analyze it, we need to include a discussion around relevance, accuracy, reliability, validity, errors, uncertainty, and limitations. And each of these areas can be included in your report. You may gloss over them and not spend too much time on them. Others you may go into a little bit more detail as you make sure that you critically evaluate your study. For this video, I thought it was better to actually talk about some of the questions that you might ask yourself or ask the data that you've been collecting to make sure that you have checked each of these areas off. So the first one, and probably the most obvious one, is about relevance. So relevance is how the data relates to the research question. The last thing we want to do is to carry out a whole lot of data collection and then realize that what data we've collected doesn't actually answer our question, or it doesn't entirely answer our question. So you need to make sure that the data does actually help you answer your question. The next thing we need to do is think about accuracy. So accuracy is how close the data is to the true value, and it's often associated with the measuring equipment. So what equipment did you use when you were doing your measurements? How accurate was that equipment? Could you have used a piece of apparatus that was more accurate or read to a tighter scale than the one that you chose? Was that not available to you? And of course, there are going to be questions around accuracy that are related to both the desire for the best equipment that you can use and the practicality of what is actually available for your use. But when you're doing accuracy, or when you're critically evaluating accuracy, you do want to think about how you collected your data, why you chose those particular measuring instruments to make sure that they've given you the most accurate values you can get. We do need to consider validity, but I think it's hard to consider validity without also considering reliability. And if for no other reason, these are two terms that students often use interchangeably, and they are not interchangeable terms. It's very important that you make sure that you separate your understanding of reliability and your tests for reliability from your tests for validity. So reliability is about repetition. Have you repeated your experiment? Have you found ways of being able to gather multiple sets of data for particular criteria? But reliability isn't just about repetition. One of the things that we can talk about is that if we repeat our experiments, they will be more reliable. Well, they're only more reliable if there's a level of consistency. And the problem with reliability and repetition is if the results are not consistent, then actually you're potentially becoming less reliable as you carry out your experiment. Maybe there's something that's affecting your results, but if there's no consistency, or if there's limited consistency, that is actually going to be a very significant contributor to an unreliable experiment or sets of results. Now that differs from validity. Think of validity as truth. Validity is about what is true. So it's partly about relevance. Does the method address the aim? So is there a relationship between method and aim? Can we link these two things together? So that is a test of relevance. But also, let's identify the three variables that we need to look at here. So we've got an independent variable, we've got a dependent variable, and then we've got a set of controlled variables. And how you control these variables. Have you actually thought about all of the potential things that could be changed in your experiment and then made sure that only the ones that you're interested in are the ones that are actually changing? Have you sometimes thought about what might be optimum? If you were growing cultures, for example, we wouldn't necessarily do that at room temperature. That may not provide optimum conditions for the growth of our culture, and therefore if we're looking at factors that might affect the growth of those cultures, we've already started behind the eight ball because we haven't been able to provide the best kind of environment. There are other experiments where room temperature would be a very good thing to control and make sure that all the experiments were carried out in the laboratory from day to day in the same general types of conditions. So thinking about controlled variables, there's not always controls that you can actually have on your variables. Room temperature is regarded as room temperature, even though between summer and winter, there might be some significant differences in the actual room temperature. We need to think about each of these things because if we are carrying experiments that are running over 6 months and across different seasons, then what we describe as room temperature may be a little bit different. So these are all of the things that you need to think about in terms of validity, in terms of when you make a conclusion, how truthful can these conclusions be based on the data that you've got and based on the method that you developed. The second set of questions that we want to look at are really about the sorts of things that can actually mean you think you've got a result that maybe addresses your hypothesis when perhaps you haven't. So you need to think about some of these questions in light of the sort of things that could potentially go wrong with your experimental procedures or at least your data collection methods. The first one is around error. And error isn't a mistake. It's not something that we just forgot to do. Error is something that's actually part of the processes, and errors will always be present to certain degrees. And so what we're not trying to do is to eliminate errors. I mean, it would be nice if we could, but the majority of the time what we're trying to do is to minimize errors. So what sort of errors are we looking for? Well, we'll talk about this in a little bit more detail in future videos, but at the moment, we think about error as the difference between the measured value and the true value, what we actually expect. So for physicists, we often talk about ignoring friction or air resistance. Well, we know those are real factors, but we also know that they are going to affect our calculations, and maybe they're going to mean that the value we calculated isn't exactly what we would expect. Same sort of thing if we're doing a combustion experiment in chemistry, for example. We might calculate a value for the enthalpy of combustion, and we compare it to the theoretical value, and we realize that actually we've lost a lot of heat to the surroundings, and so therefore we're not able to achieve that same sort of result that we might theoretically expect. So what is the difference between the measured value from your experiment and the true value? What would the real value be in perfect circumstances? What sort of errors might be present in your data? And yes, human error can be one. If it's a systematic error, it may be something that's you might be consistently reading a scale using parallax error, not looking at it straight on, but maybe looking from an angle. But if you consistently look at it from the same angle, then you're making the same error all the time. There are also random errors that can creep in as well. So think about the difference between systematic errors and random errors, things that can kind of just crop up from time to time. Maybe you left a window open and there was a breeze coming through and you didn't realize that was the case. You might have walked into the room after a previous class had been in there and didn't realize there was something else that maybe was actually having an effect on your results. We can separate error from uncertainty, and uncertainty is the range in which the true value is likely to reside. So this is where you might start using things like error bars. So instead of plotting a data point, you might plot a point that has some degree of error associated with it, which recognizes, say, the limit of reading of your device. So usually we regard that as half of the minimal scale. So if you think about a ruler, a 30 centimeter ruler, which is measured out in millimeters, you can probably work out something could be 1.5 millimeters. That's sort of halfway between those little gradations, but you can't do 1.2. It's just too difficult to try and break up this little tiny space into 10 equal segments and work out exactly where that 2/10 would be. That's the sort of thing where we have a limitation in our device and we have to think about how that might affect our measurements, particularly if we're going to then do calculations. We're going to potentially magnify some of those errors as we put them into different mathematical equations and so on. So for uncertainty, what's the range in which the true value is likely to reside? And are we likely to find that with the equipment that we're using? How have you considered uncertainty in your measurements? And also, when you start to analyze some of these results, what sort of standard deviation is evident in your data? We've talked previously about the fact that standard deviation is about variability or variance. And if you have a very wide span of data, you're going to have a large standard deviation, and potentially you're going to have lots of different outliers maybe in this data. That's not as good a data set, particularly if you're trying to measure something consistently, as if you have a small standard deviation. A lot of the values are very close together and you're getting some nice consistency. If you're a chemist, think about titration, for example. We don't want to do a titration and have ranges of values 1 to 2 mils apart. With a device like a burette, we should be able to get way more accurate measures than that. So that would create a mean and a standard deviation, which would be way too big to make the sample valid. Finally, a few limitations you might like to think about as well. What sort of factors do you think might affect your interpretation of the data? And this could be something like bias. Are you carrying something already in there where you're looking for a particular outcome and maybe you're thinking about the results in that context rather than trying to look at them objectively? What factors might affect the validity of your data? And we talked about that earlier. And so some of the things to think about include sample size, the number of repetitions, your experimental design, any external factors. We'll talk about confounding factors next. Limitations of your measuring instruments, or maybe some of the simulations that you're using and anything that's been part of their design that you think might have had an impact on the collection of your results. Assessing data is an area where in your discussion you'll have a lot of information that will critically evaluate your methodology, the results that you've got, and how much confidence you can have in their interpretation. So it's definitely worth considering these factors. Thanks for watching.